Hi everyone. We left off talking about heat capacity and a bunch of the equations for ideal gases, just coming up with more ways of kind of proving equations we already had. So we'll continue on with that by doing a few practice questions with the heat capacity. So pause video, work on the self, and we'll go over in a second. All right, so what they want us to do is they want us to take this thermodynamic identity and integrate it so that we get this. So we have a good starting point and we have a good ending point. Now all we have to do is try to get from here to here. Now, what we're going to have to do is we're going to have to figure out what this term is, what this term is, and we're also going to have to rewrite P over tau in terms of V so that we can actually integrate it. So starting with the internal energy, the base equation for internal energy for an ideal gas is 3 halves n tau. Taking the partial with respect to tau gives us 3 halves n, which we're going to want to substitute as CV, as the final answer has that as a term. So we end up having that. Now for this, going back to our internal energy equation, we need to rewrite this, take the partial of this with respect to V. Now, if they didn't make this distinction that the temperature in this specific case is constant, then what I would have had to do is plug in the ideal gas law so that I would be able to have something for the internal energy as a function of volume. But in this specific case, since the temperature is constant and the number of molecules are constant, that means that if I take the partial with respect to volume of this equation, it's just zero. And then this, I'm going to basically replace the pressure with n tau over V. Or you could have also just replaced the pressure times P over tau with just n over V. Either way, you'll end up getting the same answer. So plug everything we have into here, and now we have a very nice, clean setup. Something that's going to make be very easy to integrate, because now we have tau and d tau, v and dv here, and as we know, the nice integration of this is that it's always going to end up being an ln function. So we end up getting cv times the integral of this, which is just ln tau, plus n times the integral of this, ln v. And then, as always, when you're doing an indefinite integral, you always have that constant at the very end. All right. Here's the next question. Trying to find the average pressure in a system. Pause the video, work on the stuff, and we'll go over in a second. All right. So what we're going to want to do is remember we have an equation for pressure given by this. That pressure is the partial derivative of the average energy with respect to volume. Now, what I can do is I can actually take this one step a little bit further and make a distinction that the pressure at a specific state of a specific system is the same thing for the energy at a specific state or a specific system. By making this distinction, I can then go back and use my definition for average of anything by doing a weighted sum of all the pressures. So I do pressure at a specific state or system times the probability of it being at that state. So from there, I plug in what I got up here for the pressure, and then also the probability is that whole Boltzmann factor divided by the partition function. Clearly, that's one of the ways I'm going through this, and I get to the final answer. So for the most part, when you see this, you probably should have recognized that we're going to do something like this, that we're going to do some sort of sum of the pressure times the Boltzmann factor divided by the partition. So the only trick was to actually see, well, how can I get the pressure to look something like this? One of the things that you will just have to kind of remember is the way that we change the symbols for energy. all roughly the same, but just find something that relates pressure with energy and see if you could get something that looks like this, and that's pretty much it. All right, so for part B, they want us to find this. So pause the video, work on this stuff, and we'll go over in a second. All right. So the way we're gonna do this is we're gonna go back and try to come up with an equation that we can take for energy and take the partial with respect to V. So for example, I have this. There is a relationship that we had from one of the previous slides that we had that was given as this. There are other things involved too, but all that really matters was that the energy ended up being proportional to L to the negative 2. Now, I need this rewritten in terms of volume so I could take the partial. So what I'm going to do is remember L cubed is volume. So that means L to the negative 2 is the volume to the negative 2/3. Yeah. And then what this will give me is when I take the partial of this, or I could take the ln first. It doesn't really matter. I'll end up getting the same thing. But if I take the ln of this, what's going to end up happening is, because we don't have the full equation of every other constant term that's involved, and that we only have a proportionality, by taking the ln, it kind of does the trick that I've shown you before with the, taking derivatives with ln, that you can have one term where you have the variable and then every other term is just put into a constant section. So that's what it's saying here. So this is that proportionality of relating to the volume, and then this constant is referring to the ln of all this stuff plus some of the other things that isn't included in here. But all that we really care about though is energy's relationship to the volume. So taking the partial of this with respect to volume, well, this just becomes 1 over E times the partial of E, and then this becomes 1 over V plus 0, and then just moving things around, and we get exactly where we want at the very end. All right. Here's the next question. Pause the video, work on stuff, and we'll go over in a second. Alright, so from here, what we're going to do now is, they gave us part A and part B so that we can bring them all together and actually analyze the equation for the average pressure. So remember, from part A we had this, and then from part B we figured out what this partial derivative term is. It was equal to this. So what I can do is I can now actually simplify this a bit. The negative 2/3 V doesn't really matter, so I can pull them out, and then I'm left with this. But wait a minute, sum of energy times a Boltzmann factor over the partition function, or another way of saying it, a weighted sum of the energies. This is just the average energy right here. So this part can be replaced with average energy, or being substituted in with the U. Because remember, U and average energy are essentially the same thing. So there we go. We end up getting to this final answer that they wanted. All right. So continuing on, we're going to talk a little bit about internal degrees of freedom. So so far, the things that we mentioned, I said before that we're only really focusing on what we call monatomic gases. And by doing this, the monatomic gases are limited to only 3 types of translational energies, 3 degrees of freedom, if you will. Now, even though we haven't really talked a lot about polyatomic gases like diatomic, triatomic, something like H2 or O2, we could still take questions with them, but we would make the distinction that we're talking about low energy states. ones that where the polyatomic gases are only limited to their translational motion. And we haven't really discussed any of the higher degrees of freedom. So now what we're going to do is we're going to try and find a way of how can we actually incorporate these higher levels, the rotational and the vibrational degrees of freedom. Now, to make our lives easy, what we're going to do is we're going to split the energy of the molecules into two parts. One part's going to be the translational energy, and the other is going to be the other ones, which we're going to call the internal energy. So the rotational and the vibrational. The reason why we're doing this is because we already have equations dealing with the translational energy. Now what we'll have is just a little extension to every equation that's now going to be in terms of this new internal energy. So this is what we end up getting, that the total energy is made up of the translational motion and the rotational and vibrational motion. All right, so our Gibbs sum is going to look something like this. But we're going to have, so we had this sum before being like 1 plus lambda e to the epsilon n. But now that we're also including internal, this sum, we're going to have to include that sum in again, this time dealing with the internal motion, internal degrees of freedom. So this part, this translational part is completely independent, so it can be pulled out of the summation, and we end up getting this. And then what we're going to actually define this term as is the internal partition function. Because remember, the partition function was the sum of e to the energy over tau. So because we're talking specifically about internal energy, we'll just call this the internal partition. That means that the when we find the probability or the occupancy, it'll look something like this, and it will end up simplifying to look like this. Now, what we can do is we could go back to some of the other equations, and we could take our new equation for the occupancy and for the grand partition function, and basically get all the other equations, but this time now for polyatomic of higher orders. So the activity, instead of being n over nq, is now n over nq times z internal. The chemical potential, instead of just being tau ln n over nq, it's now minus ln z internal. And same thing for the free energy and the entropy. Again, only really focusing on this part, the internal sections. So realistically, the main thing is, like I said, it's a slight extension to what we've already done. So we're either adding a new term, we're basically just adding a new term. And then if we wanted to do things more focused specifically on like the free energy of the internal structure, then it ends up having the exact same structure as the original equations. All right, so we'll do some practice questions with this. So pause the video, work on stuff, and we'll go over in a second. All right, so here they want us, they give us the partition function for the internal degrees of freedom. And they want us to find the free energy, this entropy, and the chemical potential. So all pretty straightforward. As we know, the free energy was just going to be ln of this partition function. So we just plug it straight in. Nothing really crazy on that. Once we have the free energy, we take the partial of this with respect to tau, and we get the entropy. Pretty easy, since what's inside this ln function is not temperature dependent. So we're just taking the partial of this, which is just 1. And then the chemical potential, all we have to do is plug this into our equation for the potential energy, with the internal extension. And that's it. Now, I do also want to point out really quick is that in most questions, I would have told you that you can have your answer in terms of tau, n, and nq. Sometimes it could be a little bit tricky with the questions in the book about what variables you're allowed to answer in. Um, like the way this is written, it almost makes it seem like it can only be written in terms of I. Um, but on the test, I would be a little bit more specific and say, these are all the variables you can use. You can answer in terms of n and q, or maybe I'd want you to answer in terms of m and n and v and all those things. So you'll know what variables you actually can keep and which ones you would have to plug in. All right. I guess I'll just start the discussion on this. We have a lot of practice questions dealing with this topic. I guess I'll save a lot of those practice questions with the third video. All right. So we're going to talk about a reversible isothermal expansion. So let's consider a case where we have a gas or a system of n atoms. It starts with some initial volume at a temperature. Now we're going to allow it to expand, and we're going to allow it to expand in such a way that the temperature remains constant. Now, what we mean by reversible, I'm pretty sure I mentioned this already, but reversible processes are ideal processes. They're not things that can happen in the real world. Typically, reversible processes occur over an infinitely long amount of time. And the reason why we call it reversible is that at any moment, we can pretty much stop the process and make some measurements and find that it's always in the most probable configuration, um, or always in that equilibrium state of equal um, the entropy. So the reason why this is something that doesn't happen in the real world is because when you go through a process, usually in between the initial state and the final state, there'll be dips, highs, and lows. Maybe it won't stay in the most probable configuration. It will end up spiking or going to a different configuration. So it's not always going to be in equilibrium. The way I kind of consider it or think of it is kind of like how in a lot of questions, when you have an object that starts from zero and then starts accelerating, we just assume that that acceleration is constant. But in real life, there's a jerk to that acceleration. There'll be a usually like almost like an immediate spike in the acceleration before it kind of comes back into what you would normally be consider a constant acceleration. So that's kind of what's going on here. That there'll be these moments where the process occurs and the system is still in its original state and is being jerked into the next spot, and it will kind of almost lag away from the most probable configuration into one of the other ones. All right, so our pressure equation from the ideal gas law looks something like this. And we can have this relationship to figure out what is the pressure and volume at a specific state. And then our entropy as a function of volume will look something like this. So that means our change in entropy is only going to really be dependent on the volume, and it's going to be related to the volume based off of this ln function. Now we can figure out the work being done by taking the integral of p dv. We're going between volume v1 and v2, so plugging in our ideal gas law for the pressure and then integrating that, we end up getting this for the work. And then we also can figure out the change in the internal energy by looking at its equation. Since the temperature, once again, is constant, it's an isothermal process, then that means that the change in internal energy is going to be zero. Now, what we can do is we can actually combine all this to figure out what the heat added to the system was. So, because it's an isothermal process, one of the neat things about it is that the work done by the system is going to be equal to the heat added to the system. All right. Now we're going to take it to a slightly different process. This time we're going to go to what we call an isentropic process, or you may have also heard it as being called an adiabatic process. This is one where the entropy remains constant. Uh, in If you learn it being called the adiabatic process, I think the distinction for that was that it was the heat remaining constant, but here heat and entropy are related, so um, we're going to go more with the entropy definition in this case, which is why you're probably going to see it more being called isentropic. All right, so once again, we're still going from volume V1 to V2. And once again, it's going to be done in such a slow manner so that it's reversible. It's There's no heat going to be transferred, anything like that. Once again, we're going to want to come up. So our entropy now is going to be dependent on volume and temperature. So once again, if we do pretty much the same thing that we did last time, um, where we get a relationship of the entropy, it will look something like this. The change in entropy is always going to be the same. So we know the entropy at the initial state has to be equal to the entropy at the final state. So we end up getting this relationship. From here, we can actually now find a relationship between the temperature and the volume related to the other temperature and volume. With the volumes, we can actually go back and plug in the ideal gas law. So this is one equation we can use. Another thing though is in case we don't have the volume values, let's say we were given the pressures instead, we can go and plug in the ideal gas law for the volume, and our equation will then turn to look something like this. So this is another relationship that also works for isentropic processes. And once again, I could use the ideal gas law, this time plugging in for the temperature, and get a relationship with pressure and volume. So all these cases end up being same and being equally valid. It's all based off of the variables that you're given during for the process. So you're giving pressure and volume, you would end up using this. You're giving temperature and pressure, use this, and temperature and volume, use this one. Now, these exponents are actually important. They come from essentially the internal degrees of freedom. So they are kind of related to that aspect. So the way that they're rewritten is they're rewritten like this. So what we do is we incorporate this new term called gamma. Now, gamma is being defined as the heat capacity at constant pressure divided by the heat capacity at constant volume. And it turns out the reason why we're using that is it turns out that this ratio is always going to be the same depending on what type of molecule we're dealing with. So if we're dealing with monatomic gases, and monatomic gases strictly only being allowed 3 degrees of freedom, what we'll end up getting is that this gamma term for all monatomic gases is 5 over 3. When we deal with diatomic gases, that term ends up being 7 over 5 due to the degrees of freedom. And they didn't write it here, but the triatomics would end up having 9 over 7 as their gamma term. And like I said, it's something that ends up being true for all the molecules based off of their degrees of freedom. The reason being is that CV, as we've seen before, you take the internal energy and you take the partial with respect to temperature, and you end up getting three halves of something. You get that three halves term. That three halves being related to the internal degrees of freedom. CP, it turns out, always ends up equaling to essentially 1 minus these degrees of freedom, or 1 plus, sorry, 1 plus. So every time this goes up, this is going to go up by 2, essentially. So that's why it's like that. So if you have 3 degrees of freedom, then it ends up being 5 up here. Same thing for the diatomic. If it was limited to lower levels, so it was only allowed 3 degrees of freedom, most likely this would change to be 5/3. So most likely you shouldn't have to worry about that. I don't think you'll see any questions that are going to make that distinction. All right, so we can come up with some other equations so we can, use that first law of thermodynamics again. So the change in internal energy is going to be 3 halves and change in temperature. So again, what we can do is, since we have the relationship between the temperatures based off of their volumes, we can actually replace temperature 2 with that relationship, and it'll look something like this. Of course, you can rewrite this into whatever terms you want. If you want to instead rewrite it so it's in terms of the pressure, you want to get rid of the temperature so it's also pressure and volume, whatever floats your boat, it's going to be based off of whatever is given. That's why I'm not really highlighting this, because this is a form of the change in energy based off of what's provided. Going back to our first law of thermodynamics, we know this relationship, that the change in energy, internal energy, is equal to the heat added plus the work done on the gas. So we end up having this whole setup. Since the heat is 0, we just know that those two numbers are the same. So right off the bat, we can immediately find what the work is as well. All right. So we'll do a few practice questions, and then I'll save the rest for another video, another short video. So pause the video, work on the stuff, and we'll go over in a second. All right, so right off the bat, they tell us that the gas expands at a constant temperature. So that means everything I'm doing here is going to be based off of the isothermal process. So they give us the number of atoms, they give us the volume, temperature, and the final volume. So for the pressure, all we have to do is use the ideal gas law to relate them. Again, we know what these numbers are, so we plug them in, bada bing, bada boom, and we get that the final pressure ends up being 2.1 times 10 to the negative 8 pascals. For B, with the change in entropy, well, we plug that in. Again, since we have the changing of the volume, we're going to use the form that has the terms of volume, which looked like this, ln of the volume ratio. So the volume is going from 10 to the third to 2 to the third, so it's being doubled. So this just ends up being the number of molecules times ln of 2. Or this 6.9 times 10 to the 21. So this expansion does increase the entropy of the entire system by a very large amount. Once again, the work on the test, I'd want you to kind of like re-show this, but what we end up having is this equation that we had before. So we could just plug the numbers in, chug out an answer. I get the work is this, negative 28.7 joules. We already know what the change in energy is. It's going to be 0, because again, that's what an isothermal process is. No temperature change, no internal energy change. So from here, we can find the heat flowing by just using the first law, setting the change in internal energy to 0, and realizing that the heat equals the work. All right. We'll stop the video there. We'll do the rest of these questions in the next video. So if you have any questions, please let me know. Otherwise, I'll see you later.